Hello and welcome back to the course Materials in Sports. In this lecture we will explore biomimetics, the science of drawing inspiration from nature to develop innovative materials for sports, clothing and equipment. For millions of years, evolution has acted as a natural design process, refining and optimizing structures and functions for survival. By studying and mimicking these solutions, we can create advanced technologies that enhance performance, protection, and comfort in sports. So let's start with the definition of biomimetics. Biomimetics is the interdisciplinary science of studying structures, systems, and processes found in nature and applying the principle behind them to develop new materials, technologies, and designs. A well-known example of biomimicking is the lotus leaf effect. Lotus leaves always appear clean and dry, even though they grow in muddy, wet environments. And the reason is their surface is not smooth, but covered with microscopic bumps with a coating of hydrophobic wax crystals. Consequently, water droplets do not spread on the lotus leaf. Instead, they bead up into almost spherical shapes due to very high contact angles greater than 150 degrees, which is the threshold for superhydrophobicity. These minimize the contact area between water and the surface. Therefore, water drops roll off the surface of the lotus leaf, removing debris and dirt. This combination of a microtexture surface and an hydrophobic coatings has been adopted by textile technologists to develop water-resistant coating of outdoor jackets, which is called DWR, durable water repellency, or stain-resistant tablecloth. Biomimetics is particularly interesting when athletes face extreme environmental conditions. This challenge isn't new. Plants and animals have been dealing with extreme environments for millions of years, and they have developed incredibly effective ways to cope. Let's begin with the extreme cold. Here, nature offers plenty of inspiration, especially from animals that thrive in freezing environments. Take the penguin, for example. Its plumage traps tiny pockets of air, creating excellent insulation. In the picture, you can see a micrograph of a penguin feather, a complex structure of barbs and barbules that form a soft, bulky barrier, slowing down its loss. What's even more fascinating is that penguins can adjust their insulation. Depending on the outside temperature, they can increase or reduce the thickness of their plumage. On warmer days, they release some of the trapped air to lower insulation, almost like a natural thermostat. Researchers have developed shape memory polymers, SMP, that mimic penguin strategies and adapt garment thickness depending on the temperature. When we talk about clothing insulation, we can use the ISO standard 9920, which provides a way to estimate both thermal insulation and breathability of different clothing examples. Here's an extract from that standard. The outfit with the highest insulation is a typical expedition suit. Think of a down-fill, one-piece suit with a hood, combined with the thermal underwear, mittens with fleece liners, thick socks, and insulated waterproof boots. Altogether, these cover nearly the entire body, about 99% of the body, and provide insulation in the range of 3 to 4 kilo. Kilo is the unit used to measure the insulating power of clothing. You will learn more about clothing insulation in Lesson 7. Now, here's the fascinating part. That level of insulation is roughly comparable to what penguin plumage provides. Several studies I have included in the supplementary materials estimate penguin insulation, which is exactly in the very same range. However, penguins don't hold the Guinness record for insulation. If their plumage gets too thick, it can become bulky and make swimming harder. So penguins must carefully balance warmth with hydrodynamics. The real champion of insulation is the polar bear, and it's another great example of nature inspiring human design. Polar bear hair has a spongy structure that traps air inside. In the image, you can see a micrograph of a single hair showing its spongy core that helps keep the bear warm in extreme Arctic conditions. To mimic this natural structure, textile technologists have developed hollow fibers, usually polyester with a hollow core that traps a lot of air. Fibers can also be highly texturized, which means crimp is added to increase bulk and loft. Texturizing is done on synthetic fibers like polyester or nylon. Straight, smooth filaments are heated and twisted or crimped so that they form permanent waves, curls, or loops. When you combine hollow cores with texturizing, you get fibers that are exceptionally insulating. These fibers are ideal as wadding in high-performance winter jackets, providing warmth without excessive weight. At the other extreme, adapting to hot conditions is just as important for living organisms. One clever strategy is to adjust breathability based on temperature, a concept often called the pine cone effect. Just like a pine cone, which stays closed in cold weather and opens up when it's warm to release its seeds, some natural structures can expand to let heat and vapor escape when conditions get hot. In material science, this natural strategy has been copied to design thermosensitive membranes. In the figure, you can see how water vapor permeability of one of these membranes increases sharply at a specific point. That point is the glass transition temperature of the material. It's the moment when polymer shifts from a rigid, glassy solid to a softer, more elastic state with extra free volume. In simple terms, the material switches from being almost non-breathable to highly breathable just by tuning its porosity with temperature. Breathable membranes are key ingredients in sports clothing, especially rain jackets. They can be built in different ways, for example, sandwiched between two fabric layers, which is called a 3-layer or 3L construction. Laminated to an outer fabric with a light meshing side known as 2L, or even printed directly on the inside to create a protective texture, which we call 2.5L. The most famous example is Gore-Tex, a brand that makes membrane and laminates widely used in waterproof, breathable outdoor gear. Another strategy, also coming from nature, is changing color of the surface of garments to absorb or shield radiative heat. This method is used by insects, fish, amphibians, and also by algae, with the goal of protecting themselves from heat stress. Thermosensitive pigments can be used in textile technology to produce color-changing effects depending on temperature. In the supplementary material to this lecture, you will find a short clip showing a heat-reactive jacket produced by Stone Island. The last example I would like to discuss in biomimetics is cheetah flex foot, which is a prosthesis used by amputee runners. The name itself says this device has been inspired by the cheetah foot, one of the fastest animals on Earth. Flex foot prosthetics were invented by amputee runner Van Phillips in the early 80s. He was not happy with the prosthetics available to him, and he began to explore carbon fiber composites. The C-shaped segment, whose design is based on the rear foot of a cheetah, store energy, compressing and springing back, propelling the runner forward. It's definitely more effective than a human leg in propulsion. This prosthesis is now used in all Paralympic running competition, and Tom Whitaker, an amputee climber, was the first disabled person to reach the top of Mount Everest by using one of these flex foot in 1998. We have now reached the end of this lecture, and as always, I would like to leave you with a short recap of the key ideas. What we have seen is that nature has always been and still is a powerful source of inspiration for sport technologists. By studying how living organisms adapt to the harshest environments, we have been able to translate those strategies into innovative materials and designs. These biomimetic solutions have not only advanced sport equipment and clothing, but they are also allowed athletes to push past previous limits, taking on challenges that once seemed impossible. By learning from the solutions already perfected in nature, we can keep enabling athletes to achieve their very best. Thank you for listening, and see you soon for the next lecture.